How exactly do we make the darkest carbon glow? It sounds kind of like a magic trick, right? But it's actually pure, rigorous photophysics. Now, as you probably already know, graphene is an absolute superstar material. It's renowned for its incredible strength and conductivity. But it has a massive PR problem when it comes to optics. It is completely dark. It has absolutely zero intrinsic fluorescence. So, throughout this explainer, we're going to treat that lack of light as a problem to be solved. We're going to zoom all the way down to the atomic level to see exactly how materials scientists literally engineer light out of total darkness. To kick things off, we need to be really precise about what we're working with here. Check out the contrast. On one side, we have graphene quantum dots, or GQDs, which are fundamentally carbon-based. They rely on intrinsic fluorescence that's generated right from the carbon lattice itself. On the flip side, we have mexene quantum dots. Now, mexenes are undeniably fascinating, for sure, but their fluorescence mostly comes from metal-derived surface states. Today, we're strictly focusing on the carbon side of things. We want to understand the true intrinsic carbon evolution of GQDs. So let's start with the macro view. Picture a massive, dark gray sheet of starting material, bulk graphene. It's a perfectly continuous hexagonal sp2 carbon lattice. And because it's this perfectly continuous electronic band, it features a characteristic Dirac cone with a zero band gap. Those electrons forming that delocalized pi electron cloud, they can just move freely across the entire lattice. That's actually exactly why it has such amazing electrical conductivity. But because those electrons roam entirely free, it completely suppresses what we call radiative recombination. Basically, perfectly intact bulk graphene is fundamentally dark. It gives off absolutely no intrinsic fluorescence whatsoever. So how do we even begin to change its identity? Well, imagine we're a camera, zooming in, tighter and tighter, physically breaking this material down. We take that vast bulk graphene sheet and subject it to nanoscale fragmentation. We just keep continuously shrinking this down until we're left with a tiny isolated particle. A graphene quantum dot that's just, 2 to 10 nanometers in size. By dramatically reducing its dimensions and cranking up its edge-to-volume ratio, we are completely altering its physical and electronic destiny. And this brilliantly illustrates the core physics behind that shrinking process, quantum confinement. This is the phenomenon that literally changes everything. When the physical size of our carbon particle gets so incredibly small that it approaches the exciton Bohr radius, a massive shift happens. Those continuous energy bands we just talked about in bulk graphene, where electrons could wander anywhere without restriction, they literally split apart. They split into discrete molecular-like states. By confining the particle in physical space, we force its available energy levels to become highly specific and quantized. Let's look at the direct energetic result of that physical confinement. As the particle size shrinks, the band gap opens up. We transform from that zero band gap Dirac cone into an effective widened gap where electrons are now spatially confined between a distinct valence band and a conduction band. This is absolutely crucial, folks. It's the foundational requirement for our dot to glow. Without this gap, electrons can't absorb energy to jump up and subsequently fall back down to release a photon. By making the particle infinitesimally small, we've basically built the energetic stage for light to be produced. Now, what's really fascinating is what happens at the physical borders of our newly minted quantum dot. When we fragmented that large sheet, we didn't just make it smaller, we created massive amounts of new edges, specifically what chemists define as armchair and zigzag edges. Because the dot is so tiny, it has a phenomenally high edge-to-volume ratio. And those pi electrons that used to roam free across the bulk sheet, well, many of them become trapped. They get localized right at these zigzag and armchair boundaries. These trapped electrons form our very first edge-emissive centers, acting as localized electronic states that actively participate in fluorescence. But the evolution to brightness doesn't stop there. Notice those surface groups hydroxyl, carboxyl, carbonyl, and epoxy? By deliberately oxidizing the surface of the GQD, we introduce these functional groups. And what they do is create highly localized defect states directly inside that band gap we just opened up. These surface defects are incredibly valuable because they provide additional alternative pathways for electrons to transition and recombine. We're literally layering in more and more structural features that serve as emissive states for light. It's like a giant puzzle coming together. Section 1. Intrinsic modifications versus post-synthetic enhancements. The architecture analogy. So the crucial point is, to truly understand how we engineer these dots, we need to draw a firm line in the sand between two very different approaches: intrinsic modifications versus post-synthetic enhancements. I actually love to think of this as the architecture versus interior design analogy. It's a vital distinction in nanomaterials for ensuring scientific accuracy. Intrinsic modifications, like quantum confinement, edge states, and heteroatom doping, they fundamentally modify the internal sp2 carbon lattice architecture. Think of it like knocking down structural walls and rebuilding the foundation of a house. Post-synthetic treatments, on the other hand, represent things like polymer functionalization used simply to passivate the surface. That is like applying a highly protective coat of paint. It protects and improves the house, sure, but it fundamentally leaves the underlying architecture completely unchanged. Let's look a bit closer at that intrinsic architectural change. When we talk about intrinsic evolution through doping, we're zooming all the way down to the lattice level. We're literally swapping out a black carbon atom for a completely different atom inside the sp2 framework. This is substitutional doping. Because we're changing the actual atomic building blocks of the framework, we directly and permanently modify the intrinsic electronic structure and the charge distribution. This gives us immense, precise control over the exciton dynamics and the fluorescence generation itself. It is a real game changer. Let's see how this builds our tunable color palette. If we swap a carbon for a nitrogen atom, we increase electron density. That improves conductivity and yields a much higher quantum yield. Swap it for a sulfur atom, and we introduce specific donor states that give us a beautiful red-shifted emission. A phosphorus atom is physically larger than carbon, right? So squeezing it in causes lattice distortion, which is actually perfect for trap state and bandgap engineering. And a boron atom acts as an electron-deficient acceptor, increasing hole density. Each of these foundational atomic swaps dictates specific emission colors and optimizes the exciton dynamics from the inside out. Now, let's drastically shift gears and contrast that with post-synthetic enhancements. This strategy involves coating or conjugating the quantum dot with polymers, for example, using polyethylenamine or PEI, or using polyethylene glycol, PEG. So, what do these actually do? Well, they pacify existing surface defects, dramatically alter the surface chemistry, and massively improve the stability and sensing performance of the dot in various environments. But please note this detail very carefully. It does not change the sp2 carbon framework. Post-synthetic strategies are incredible for protecting the dot and making it useful for biological applications, but the foundational carbon wiring driving the fluorescence remains exactly as it was. We've explored the structural setup, so let's bring this cinematic journey to its energetic climax. We've shrunk the graphene, opened the band gap, localized the electrons at the edges, added oxygen defects, and engineered the lattice with heteroatoms. So what actually happens when a photon of light strikes this masterpiece? Follow the energy path here. The electron absorbs a photon and gets excited all the way up to a higher excited state, S2. It then undergoes a non-radiative internal conversion, dropping down slightly in energy to settle at the lowest excited state, S1. Finally, the magic happens. Radiative relaxation. The electron falls back across that engineered band gap to the ground state, and in doing so, it releases a brilliant cyan photon. We have officially transformed a dark, non-fluorescent continuous sheet of carbon into a perfectly engineered, glowing point of light.